Good morning everyone. In this lecture, we will briefly discuss about the different types of controllers or compensators and what is this compensator is and what are the different compensators or controllers available and what are the basic functionalities of this. This is the main objective of this sections. That means in this class we will discuss this. Now see, all you know the basic block diagram of a feedback control system. What is the function of feedback? Already you know. The system is open loop, so that is in that case the output cannot be controlled from the input side. So in order to have the access of the output in every time from the input side such that the desired output can be obtained, that is the function of feedback system. So feedback control system is this, and you see there is I have written some dotted line here. That means there is some other element too. And once you can remember the closed loops, the generalized block diagram of in control system, that means feedback control system, negative feedback control system, you see there is a plant which is to be controlled, and definitely there is certain kind of, you see, extra block is there which is normally known as GCS, and the signal which it's actually received, that is the error signal, right? Error means what? Error means we know till date already we know everything, that is the input minus output, that is RS minus CS is coming here, and that is the error. That means if there is an error between the input and output, that means you are not going to get the desired output. So in order to get the desired output, error must be less, because this is your desired signal. Say this is your desired signal input, right? This is your amplitude, this is your time, and you are getting the output is like this. So that means there is an error between these two signals. So this error is to be minimized. How to minimize this? By using some controller, right? So this is the function of controller or compensator. We can say it compensator. Sometimes this is maybe controller. So once you know the different types of controllers are used depending upon their functionalities, and they will take the error signal as the input and finally take some necessary actions, and it gives him output signal which goes to the actuator. You know, this actuator will actuate the system such that your desired output is reached. That is the purpose of the control system, and that is the purpose of the compensator or controller. This is the compensator. So this is the compensator block. Now normally there are and the two types of compensator are used. One is series type of compensator, one is parallel type of compensator. That means this is kind of series type of compensator. You know, this can be treated as, or it can be said as the series type of compensator. What does it mean? Does it mean this is basically one kind of series? This is series compensator. Series compensator means plant is in directly cascadely connected with this, and there is another version which is the parallel type of compensator, where this compensator will be connected in parallel to this plant that I will show here. See here I am showing one kind of parallel type of compensator. Just a structure here I am showing. This GP and GS are in like this type of feedback path is actually used here to give the structure like parallel compensations. That means if there is a cascade connection between the GPNs and GCS, that is the compensator and the plant, that is the series compensation. If there is a feedback path like this and they are like parallelly connected, so this is the parallel type of compensator used in the case of normally industrial versions. So either series compensation or parallel compensations, there are normally three types of or four types of, I can see it, four types of compensation techniques are used. We will discuss it one by one. Here first of all we will discuss about a type of compensator normally known as lead type of compensator. By the term you see lead compensator, what does it mean? It means if you apply it to the input of any compensator. So the compensation lead type compensator structure is like this, where I have drawn the structure with the help of some electrical parameters or electrical systems, right? You see this is C and R, they are parallel in this path, and R2 is there, and V0 is that means output voltage is taken from here, and here is your input voltage. And normally in case of this type of lead compensator or lag compensator, I am a lead lag compensator I am going to discuss about. In all these three cases, normally at the input side we are applying certain kind of sinusoidal signal. So sinusoidal signals means it is having some phase and frequencies, all these things, the parameters of the signal, and you see, if this is a kind of lead compensator, what happens normally at the output side, this output will be phase lead with respect to input. So this is the concept of lead compensator, and depending upon the different plants given to you, and to get actually what is the function of the compensator, we know, to get the system stable. First of all, in order to get the system stable, what are the different conditions, from the time response characteristics, the time response characteristics are there, like rise time, peak time, maximum peak overshoot, you can remember all these things, and the steady state error, right? Settling time. So settling time, steady state error, maximum peak overshoot, rise time, and peak time, these are the time domain specifications. And in the frequency domain specifications, we know what are the different kinds of specifications, the phase margin, gain margin, or all these parameters, right? So in order to give a perfect value of that, that means if you want to get the plant such that its maximum peak overshoot maybe 10%, maybe you want to get the settling time set as 1 second, maybe you want to get the system steady state error is only 0.5%. I want to say that these are the specifications of a system output you want to get. So according to that, you have to design either lead compensator or lag compensator or PID controllers, right? So PID controllers are normally one kind of controller which is majorly used in the industrial versions, but these are all falling in the category of compensator. Either this is sometimes known as controllers, sometimes known as compensators. So compensators design techniques are different. So here in our syllabus also, we want to know what is the kind of lead compensator. Lead compensator means input is like this, so output is like this. That means output is having a phase lead with respect to input, and this is the structure of the lead compensator, and this is the transfer function. This is the general transfer function actually, not for the lead. And for lag type compensator, this is also true, but when you get, say, this is the S is equal to minus Z is the pole positions, and S is equal to minus P, sorry, this is 0 position and this is pole positions, and see, this is your 0 position and this is your pole positions. That means if the poles are far away from the 0 at the left hand side of the imaginary axis. So if, say for example, S plus 5 by S plus 10, see, this is the one of the compensated module is given. Here you see the position of the 0 is minus 5 and position of the pole is minus 10. That means position of the pole is far left from this 0. So this is the kind of structure which is the structure of the lead compensator. Now once you call it as lead compensation, definitely there are some functionalities of it, and what are the major effect, or you can say the advantage. First of all, you get the speed of the system is increased. Number one, speed of the system is increased, and number two, overshoot of the system is decreased, right? Overshoot of the system is decreased. So these are the two major advantage, or the you can say it effect. Speed of response increase, that means system becomes faster. Number two is you can tell it overshoot decreased. So what to decrease, and speed of the response is increased, or in certain cases you want to have these two types of behavior at the output system. So in that case you need to use the lead type of compensator, right? Next I will discuss about the lag compensator structure and its transfer function, pole zero form, and advantage or effect, right? So here you see, this is the type of I can say it the lag type of compensator, and the same thing is like that of the phase lead type of compensator. This is sometimes known as phase lag or phase lead. So phase lag compensator means the phase of the output system once you apply any sinusoidal input of certain phase or frequency at the input side of this network. So network is that here the capacitor block comes in this plot, and in this block where you are getting the output. So this is R and C and parallel series, and in case of lead compensator the structure was R and C was parallel here, right, and output was measured across the resistance. So here the same type of compensator, this is transfer function is given where there is a normal structure where there is a pole and there is a 0, there is a pole and 0, and see, you see pole is at minus z and pole is at minus p and z is at minus z, 0. So here I just take the pole 0 configurations of any lag type compensator, where you see the structure is like, you can get is like s plus 2 by s plus 0.2. That means the pole is more closer to the imaginary axis, or this s plane, this 0 origin, and 0 is situated far away from pole on the left hand side. So this is the actually basic difference between the lag compensator and lead compensator. And once you are using this phase lag type of compensator, so definitely there will be certain advantage or effects. Here actually you will see the gain crossover frequency increases, right? Gain crossover frequency increases and bandwidth actually decreases, and response will be less in case of this. But the advantage is that the frequency it allows the low frequency and high frequency and actually attenuated. That means one kind of this is, you see, one kind of filter. So if this is one kind of filter, that means the low frequencies, this is kind of low pass filter actually, I can better say it. Low pass filter means it allows the low frequency part and it blocks the high frequency part, or sometimes it actually trying to attenuate this part. And due to the present of actually this is kind of lag compensator, what happens, the steady state accuracy is increased. Steady state accuracy is increased means the error is actually decreased. So overall the effect I can show you the effect like this: the gain crossover frequency increases and bandwidth decreases. So gain crossover frequency increases and bandwidth decreases. And number 3 advantage we have already on. This is a kind of low pass frequency, low pass filter, act like low pass filter. That means it passes low frequency and attenuates high frequency, right? So high frequency are getting attenuated and passing the low frequency. And number 4, this steady state accuracy is increased. Steady state accuracy increased, right? So these are the major advantage of lag compensator. And in this lead or lag compensator, sometimes these two kinds of operations are simultaneously required. In that case, we will have to have the compensator like, which is known as lead lag compensator. But lead lag or lead lag compensation, in both the 3 cases, what happens normally, this is kind of frequency domain analysis. That means you are going to apply the frequency input, that means the sinusoidal input, and you are going to get the sinusoidal output, and that lead and lag of the phase corresponding to the input signal and output signal will be studied here. And you see this the actually response characteristics, and see the advantage and effects I have already discussed. And when both the two are amalgamated together, then we will get the lead or lag compensator, right? So here I will see the structure of the lead and lag compensator. Here, and this is the structure of the lead lag compensator, where you see the lead part, that means R and C are parallel here, and R2 and C2, these are series connected, where output is considered is across R and C. This is the lag part, then this is the lead part. So in the advantage of the lead part and lag part, both are considered here. First of all, speed of response is increased. Speed of response increased. And number 2, accuracy is also increased. That means error is decreased. So there's 2 parts. You can get the transient parameters, the transient behavior and steady state behavior. So speed of response is increased, that means transient behavior increased and the settling time is decreased. First it is going to get settled down, and once it gets settled down, the error is also decreased. That means accuracy of the system is increased. That means you are going to get more accurate output what is your desired value. So in the advantage of lead network and lag networks are both coming into the system, which is known as the lead lag compensator. So depending upon the different plants and different operations, different requirement of the output, we are going to get different ways of compensator. Number fourth is, which is known as controller. Basically controller is one kind of compensator, and that is normally connected in series with the plant. And there are normally PID type of controller, where you get the three actions: proportional actions, integral actions, and the derivative actions. So in industrial versions, normally PI controller, PD controller, and PID controller, these three combinations of the controllers are used, and most widely used controllers are PID controllers. We will discuss it in a bit. Here we will discuss about the controllers, and this controller is normally connected with the plant, and this controller takes actions on the error, right? Error already we have discussed, that is the error means the difference between input and output. So there are different kinds of actions, and based on the actions we are going to get the different kinds of controllers. This name is proportional, integration, derivative, proportional plus integral, proportional plus derivative, and proportional plus integration plus derivative controller. So see, step by step I will discuss what are the different functions of the different types of controllers normally used. So first of all, this proportional control. So what is the function of the proportional control? In case of, if you apply only a P controller here, so what does it mean? That means it is the output of it, say this is Y. So output of the controller is say Y, and this for proportional controller, the output is normally is proportional to the you see this is error, proportional to error. So this is proportional to error. That means this Y is equal to Kp into E. Mathematically we can say it, Y is equal to Kp into E. Kp into E means this is your proportional constant. So this is your proportional constant, right? And this is the actions, that is the function of this proportional controller. Similarly, for I type controller is the error corresponding to this Y output is based on the integration of 1 by Ti, that is reset time, E dt. That means what the time 0 to T, maybe some certain interval is given to the controller, and it takes some error based on certain time, and it integrates this value 1 by Ti. That means sometime this is known as Ki into, you can say it, 0 to T E dt, and this is known as the integration constant. And for D actions, you see this is error, and based on this error, some mathematical calculations like this is proportional to derivative of the error. That means Y is equal to Kd dt, and this is your derivative constant, right? So these are the three actions. You see, once the error is obtained, and based on the action of the different types of controllers, for proportional controller there is the output of the controller is proportional to the error. For integration controller, output is proportional to the integration of the error over a particular time interval, and for derivative controller, output is proportional to the derivative of the error. That means, and to remove the proportionality constant, we have used three constants. One is known as Kp, one is known as Ki, one is known as Kd. Now the setting of this Kp, Ki and Kd are very important, because once you write any controller, for example any PI controller means there will be two actions, one is P actions, one is I actions. For PD controller, one is P actions, one is D actions. These two actions will be combined. And for PID controller, which is the most important and industrial version of the PID controller, that is known as the PID controller, that is proportional, integration and derivative controller. This controller takes the advantage of the proportional controller, takes the advantage of integration controller, and takes the advantage of the derivative controller. And this is the majorly used controller in the industry nowadays, from the starting where the industrial controllers have been started using for controlling defined parameters, right? So this is the basic formalities, and this is the different types of controllers. Now I will just explain some of the advantage of using proportional actions, using integration actions, using derivative actions one by one. So two major functions of using the proportional constant is that this will try to make the system more stable in the sense it will try to reduce the steady state error. It will try to reduce the steady state error. Once the steady state error is reduced, this will be more stable. And definitely once the system is sometime becomes over damped, so in case of over damped system, what happens, these controllers actually use this part and makes the system faster. That means the more stable system and faster type of operations, these are the two major functionalities of the you see this is the proportional controller. And proportional controller, I will just write the structure of the proportional controller, how this proportional controller can be used to the plant. See, this is a kind of proportional controller. This is a type of proportional controller used here. What is this? This is basically one gain, right? Proportional means it is proportional to the error, and is proportional to error. So this is the output of it, that is k into e, right? This may be kp, and if you just multiply the transfer function of the plant with this, you know this is the nothing but the gain. And once you vary the gain, you see there are from the rule locus or from the route area, from the time response, you see from the variation of the gain what happens. You get the system either stable or system maybe unstable, and like that. So these are the basically here in case of proportional controller, you can add integrator controller, you can add derivative controller, you can add PD controller, you can add PID controller, you can add PI type of controller. So next the thing is that what is the function of integration controller advantage. What are the actually advantage? It tends to make system actually response it actually works on the steady state response. That means the steady state this I controller, I actions, I can say it I actions means integration actions will make the system response better in the steady state domain. That means the steady state error is decreased, steady state error is reduced. Steady state error is reduced, that means the accuracy of the system is better. And you see for D action, that means for derivative actions, what happens in case of derivative actions, this is basically this improves the transient performance of the system, transient performance of the system, but it never improves the steady state error. So steady state error cannot be reached, but it improves the transient response. Means say for example, if there is certain overshoot, so overshoot may be decreased by using the D actions, right? So overshoot may be decreased by using the D actions. Steady state error can be reduced by action this I controller, and that means the actions of the proportional control have been discussed. So depending upon the situations, maybe your transient response behavior is to be improved. So in that case, you can go for PD controller. Maybe the steady state parameters you have to increase. In that case, you have to go for PI controller, and certain time PID controllers are used. But nowadays, the study shows that PI controller are the most suitable controller normally in case. And if you use this PI controller, mainly the purpose of better stable system can be achieved if there is no so much overshoot in the system. That means if the transient parameters the transient behaviors are not so poor, so PI controller will be sufficient instead of PID controller, or in certain cases PID controller can be also used. Now the thing is that once you coming to the design of the controller, next is the design of the PID controller. Design of the PID controller means what? PID controller, design of the PID controller means what? That I will discuss in brief. See here, I have written a block. Where you see, we have written a block of PID controller. This is PID controller, right? So if this is a PID controller, that means that is KP, KI and KD. These are the three elements which will be present. And you see, this is KP means KP into E, KD means KD into d dt, and I actions means ki into edt. So in order to get the transfer function of the controller, what you have to get, we have to get the Laplace transform of both these things. So that is your output of the controller, and it is the error, that is the input of the controller. So ys by es, if you get, so kp into es, this is kd into acs, this is ki into es by s. So if you just go on getting the output of this, that means these three will be added together to get you the PID controller, and ys by es, that will be your GCS, that is the controller transfer functions, that is kp plus kd into s plus ki by s. You see, this is the transfer functions. Now when any plant is to be controlled, first of all you have to design this controller. Design means what? Design means you do not know this value of kp, ki and kd. So to get the output at your desired value, what you have to do, you have to just tune this controller. What is known as tune this controller? Tune this controller means you have to set the value of kp, ki and kd, right? So if you get the optimum value of ki, maybe kp is equal to 1, ki is equal to 1, kd is equal to 0.5, for that you are getting that your steady state error is 5%, your maximum percentage of overshoot is 25%, like this. So you are getting the it's not getting the desired specification. So you have to change this kp, ki and kd, and see, definitely there is some interaction factor between these three elements. So kp, ki and kd, they are actually internally connected, or internally there is an interaction between these three. So optimum selection of kp, ki and kd is known as the tuning of the controller, for which value of kp, ki and kd will get your desired value of the output, that is the tuned value of the controller. So this is the way how so there are the different tuning rules. There is soft computing techniques are there, there are classical techniques are there. So this is not is discussed in this class. So after this we know what are the different types of controllers, what are the different types of compensators, how the structure of the compensators and controllers are designed, and what are the pole locations, what are the different transfer functions, and what are the different actions of the different types of controllers or compensators, right? So and the basic definition of the tuning, right? So this is all about the design or the introduction to compensator design. I can say it better. Thank you.